So basically, for nominal variables, we have the chi-square test of associations. And for continuous variables, if one of the variable is continuous, then we have a bivariate correlations, which are Pearson correlation, also known as Pearson product moment correlation, and Spearman correlation, which is the non-parametric correlation. It is also known as the interclass correlation. We have non-parametric Kendall-Tau correlation, biserial and point biserial correlations, and partial correlations. So if you leave chi-square test of association alone, then you can see that correlation is not only limited to Pearson or Spearman. There are uh, five types of correlations: the Pearson, Spearman, Kendall-Tau, biserial, point biserial, and partial correlations. So first we will start with the chi-square test of association. This chi-square is a test which is used as a test of association, and also in regression it is used as a goodness of fit. So it is known as the chi-square test of association when you are testing the association between nominal variables, and it is also used as chi-square test of goodness of fit when you are doing multivariate analysis like CFA or SEM model. So you might be getting values C mean. C mean by degree of freedom is nothing but the chi-square. Well, so this test BS, though it seems to be a very small, very basic test, but it bears great resemblance when it comes to testing it as a measure of goodness of fit in multivariate statistics. As a test of association, it is also known as chi-square test of independence. So let's say you have two variables which are nominal, and you want to test whether these are associated with each other or not. So please remember that for chi-square test of association, two requirements needs to be fulfilled. That both your variables, they should be nominal. None of them should be ordinal, or none of them should be uh, continuous. They should be nominal. The first thing. And second thing, when you make the cross tabulation and the contingency table, each cell, let's say if you have a variable divided into two categories, another variable divided into two categories, so it will make a 2 by 2 matrix. So we will get four quadrants or four cells. All four cells should have a minimum count of 5. So in most of the cases, if you are doing chi-square test and you are getting a value below that chi-square test, that this percent of cell have values less than 5 counts, then you can well understand that your chi-square test of association is not correct. So the basic requirement is that your in each of the cell, the minimum frequency count should be minimum 5. That's the requirement. So this test determines whether there is association between the categorical variables or not. And why we call it as the chi-square test of independence? Because based on the association, we also determine that these variables are dependent on each other or independent. If there is a relationship between these variables, then we say that they are dependent on each other. If there is no association between the categorical variables, then we say that there is no dependence, or the variables are independent of each other. That's why it is known as chi-square test of independence, also known as chi-square test of association. It is a non-parametric test, reason being both your variables are categorical in nature. And it is used to test the statistical independence or association between two or more categorical variables. So please remember that both the variable needs to be categorical for running a chi-square test. You cannot run and you should not run a chi-square test between a continuous variable and a categorical variable. Both needs to be categorical in nature. Your data must meet the following requirement, that minimum two categorical variables. Then each of the categorical variables, minimum two or more categories for each variable. Independence of observations, which is required in almost all the statistical tests, and there should be relatively large sample size. The hypothesis that we make is that the null hypothesis is that the variable 1 is independent of variable 2, and the alternative variable 1 is not independent of variable 2, or variable 1 is dependent of variable 2. So first case, null hypothesis, if variable 1 is independent of variable 2, then variable 1 and variable 2 are not associated. If variable 1 and variable 2 are not independent, means they are dependent on each other, that means they are associated. The formula for the chi-square is basically just let me take the pen. So the chi-square is represented like this, and it is equal to O minus E square upon E, where O is the observed frequency and E is the expected frequency. Observed frequency you have already calculated from your data. But how to calculate the expected frequency? That is the basic statistic behind chi-square. So this E will be equal to row total, means total number of observations in the row, into column total, number of observations in the column, upon grand total, means total of all the rows and columns. So by this you will get the expected frequency. And if you take the square of the observed frequency minus expected frequency upon divided by the expected frequency, you will get the value of the chi-square. So observed is already there, expected you can calculate, and you can get your chi-square. And please do remember that the requirements for chi-square, minimum two variables with two categories, and each cell should have a minimum count of 5. If after doing the chi-square, your result is showing that some of the cells have, or sometimes it shows that 10% of the cells or 20% of the cells does not have minimum count of 5. That simply means your chi-square is wrong. Most of the time we overlook this, because just below the chi-square table it is mentioned if this is there, but we overlook this and our results are wrong. So please keep in mind. And this will be your hypothesis. So now let's see our problem statement. Uh, in our sample data set, we had a category known as gender and a category of smoker. And we want, you can see that the gender were divided into two categories: male coded as 1, female coded as 0, and smoking was, uh, the smoking status was divided into three categories: 0 as non-smoker, 1 as past smoker, and 2 as current smoker. We want to know here that whether this smoking is dependent on the gender. Is there any relationship between the smoking status of a person and their gender? Or we want to know, is smoking dependent on gender? So here, smoking is is a dependent variable on the gender. Both are categorical variables, so we can apply a chi-square test for them. But before we go on for the chi-square, let's have a look at the initial observation, and this also can tell us whether there is a relationship or not. That is the visualization. So we should always, whenever we are analyzing any data, we should first look at the visualization of the data, that how the data is, what pattern, what trend the data is showing. This is known as exploratory data analysis. Please don't confuse it with exploratory factor analysis. Exploratory factor analysis is quite different. Exploratory data analysis is initial exploration of the data to understand the pattern of the data. That you can do by analyze and descriptive statistics, frequencies, and in charts, or you can do by another way. Yeah, not like this. Go to graph and can you see any cluster chart diagram here, or histogram? Yeah, you can select histogram. In the row, you can take gender. In the columns, you can take smoking. Sorry, take the gender in column, smoking in rows. Here, it is not making a cluster. Let me see. Bar diagram. Yeah. Okay. From bar diagram, take the clustered bar diagram. Here you can take on the rows the counts, the smoking on the rows, and gender here. It's not doing this. Let me check. It should be there, but why it's creating a problem? Because that's initial exploration will help you understand how the data is there, how the data is working. Or during cross tabulation also we can go for cluster marker. Okay, we won't go by this way. What we'll do, we will make a cross tabulation and then we can run. Okay, fine. So we have a smoking status into three categories, and we have gender into two categories, and we want to test whether gender and smoking are associated with each other or not, or whether smoking is dependent on gender or not. So go to analyze descriptive statistics and cross tabs. Here in the row, you can take gender. In the column, you can take smoking status. On statistics, you can select uh, only chi-square. And if you want, you can take phi in Kramer V. I'll tell you why we are taking this phi in Kramer V. Continue. And here only you can take display clustered bar chart. Here there is option for that. And click on OK. Now you see this chi-square test value. So the chi-square value at the degree of freedom 2 is coming to be 3.171. At this value, P is 0.205, which is non-significant. This clearly shows that there is no significant association between gender and smoking. So smoking status is independent of the gender. Null hypothesis, we are unable to reject the null hypothesis. And our null hypothesis are that both the variables are not associated. Means there is no dependence between smoking status and gender. Now, okay, here you will find that 0 cells have expected count less than 5. Means our criteria of minimum 5 counts in each of the cell is met. Otherwise, it will show that how many cells have expected count less than 5. And if even one cell is having expected count less than 5, then our result is wrong. So first thing is that the Pearson chi-square that you are getting is 3.171, which is non-significant, means how we can write it. So chi-square at the degree of freedom 2 is equal to 3.171. At this P is less than, P is greater than 0.05. So we fail to reject null hypothesis, and hence conclude that there is no association between gender and smoking status, or gender is independent of the smoking status. Sorry, smoking status is independent. Independent of gender. So this is our overall interpretation from this. Now the question is, I have asked that you can also select phi and Kramer B. Say this phi tells you that how strong this association is, if there is an association. So first thing you can see that there is no association. Since there is no association, you can also find that this, if even a little bit of association would be there, then also it is very weak, only 8.9%. Okay, so this association is very weak. So if you have 2 by 2 contingency table, means two categories in nominal, two categories in one variable and two categories in another variable, then you should look for phi. If one of the variable is having a different set of categories and another variable is having different number of categories, like in our case, the category was 2 into 3. Gender was divided into two categories, whereas smoking status was divided into three categories. So in that case, to determine the strength of the relationship, rather than looking for phi, we should look on for Kramer V. So even Kramer V is suggesting that the association is very weak and non-significant. So initially there is no association, and if you see the strength of the association, it is very weak, non-significant. When to look for phi? When you have equal number of categories in both the variables. When to look for Kramer V? When you have different categories in your variables, like 2 into 3 we had, right, in our case. So first thing, chi-square will tell you about how much your whether there is an association or not, and this phi and Kramer V will tell you that what is the strength of the relationship, if it is there, and to what level it is, whether it is a strong association or not. Like in correlation, you come to know whether the association is there or not. And then through the R value, you come to know what is the strength of that association. Similarly, here, the phi and the Kramer V will tell you that what is the strength of the association, right? And formula, I have already told you that degree of freedom, sorry, of that chi-square is equal to observed minus expected frequency upon expected frequency, where expected frequency is equal to row total into column total upon grand total. And degree of freedom in this case, because I have been telling about the degree of freedom for all the tests which we have calculated, in this case is equal to rho minus 1 into column minus 1. So we had uh, rows in three categories, that is the smokers. So 3 minus 1, 2. And columns, we had two categories, 2 minus 1, 1. So degree of freedom is equal to 2 into 1, that is 2. So our degree of freedom is coming to be 2 here. Now significant result, there is no association. The association is non-significant also, a very weak association, 8.9%. And if you see this cluster chart, you can see that the zero, okay, across genders, okay, across male and female, you can see that all the charts are very different. Okay, all the bars are very different. The smokers, non-smokers, past smokers, okay, current smokers, they don't, means they are very different, okay, from each other. That's simply across both the categories. Even this shows that there is no association. If there has been any association between gender and the smoking status, then these bars would have been equal for the both, but you can see they are very different. Okay. So there is no association. Is that clear?
Yes, sir.
Just a little clarification. You,
Sorry?
yeah, just a little clarification. You said
Yes,
that
please.
the precondition for uh, chi-square test of association is that A, the both the variables have need to they need to be categorized,
categorical.
and the cell count is
Hmm.
minimum 5.
Hmm.
What is cell count? Yeah.
So see,
Hmm.
let me draw it for you. So we had smokers, non-smokers, right?
Right.
So if I put if I put male,
Okay, so you map them.
female,
Hmm.
right?
Yeah.
And then we will be having
Three. That's right.
past smokers, sorry,
Right.
non-smokers,
Hmm.
past smokers,
Right.
and
And
current
that,
smokers.
that's it. So
So we'll
six.
be have 3 into 2 matrix. So
Six.
6 cells we will be having.
So
Each cell should have a minimum count of 5. If any of the cell won't be having a minimum count of 5, then our chi-square result will be wrong.
which means five kind of observations for each of these
Uh,
cells.
yes, yes. Minimum frequency should be 5 at least in each of the cell.
Correct. It can be 2 by 2, 3 by 2. That doesn't matter. But each of the cells have to have five count.
Yeah, how many cells have been made? Let's say if it is a 3 by 3 matrix, 9 cells, all
Right.
9 cells should have minimum.
Five.
It could be that one is having 5, another is having 12 count, but minimum 5 count is required.
So five males or five females, or similarly you have
Yes, yes,
if
yes,
if you match male to, let's say, past smokers, then in that particular cell there have to be at least five
yes,
observations.
yes, yes, yes.
That's what. Thank you.
That's why it is writing here 0 cells have expected count less than 5.
Zero.
What goes wrong with many of the people which I have found that they don't care about what is written here.
Mhm.
Most of the time it is written that okay, 2 cells, 3 cells, or this much percentage of cells have expected count less than 5.
Mhm.
That means that their that this chi-square result is wrong.
That's true.
So for that, this should be actually uh, 0 cells have expected count less than 5, and it
Yeah.
is also showing the minimum expected count in each of the cell was found to be 17.76.
Right, which is more than five.
Yeah,
Yes. Then.
and apart from reporting the chi-square test, we should also report their association.
Yeah,
Okay.
strength of association.
What is the strength of the association?
And
So
that you said were two.
so you can go for 5 when you have equal categories in
Yeah,
both
both.
the variables,
But
right?
in our case, it is not so.
If it's a situation of 2 by 2, 3 by 3, if
That's
it is a situation of 2 by 3 or 3
then
by 4,
then the
okay,
other.
then Kramer.
That's grammar.
Okay. So we will report the Kramer. So 8.9%, which is a very weak correlation and non-significant. And already which has been here suggested that there is the relationship between the smoking status and gender is non-significant. Gender has nothing to do with the smoking status.
That's
If you see the bar chart, then also.
right. And then you can go and go ahead and reconfirm by looking at each of the phi and grammar, as you said.
Yeah. Okay.
Thank you. Thank you.
One more meaningful insight this test of cross tabulation gives.
Hmm.
We all know that for continuous variables or for the Likert scale, we can do the reliability analysis by Cronbach alpha, right?
Please come again. Please
We
come.
all know
Mhm.
that we can do the reliability test for the uh, scaled data through Cronbach alpha.
Right.
But how to do the reliability analysis of categorical data?
Okay.
Right? Like you might be having data in your see, you ask some demographic question, income level,
Mhm.
gender, how to test their reliability because they are also a data and you might be using them further. Okay. So
Yes.
this cross tabulation gives you a very meaningful insight.
Mhm.
So you go to this descriptive statistics,
Mhm.
cross tabs.
Mhm.
In statistics, you will find here kappa, right?
Okay.
So if you have both the variables nominal, right?
Okay.
Then you can use this kappa.
All right. Yeah, but that is the precondition. You said that the chi-square test itself both have to be nominal variables. That's the
Hmm.
first condition. It's the
Hmm.
most fundamental condition,
Means
precondition.
this cross tabulation can be used for doing chi-square. See, if I am not selecting this chi-square, only I am doing cross tabulation, right?
Okay. Mm,
Only I have to select contingency coefficient and cross tabulation will be done. If
okay.
I want to test the association chi-square, if I want to test the strength and degree of the association, Fry and Kramer will.
Correct.
Okay.
Mm.
But this also gives you a very meaningful insight that if you want to test the reliability of the
Okay.
categorical variable,
Okay. Okay.
because for scaled variable, we all know that there is a Cronbach alpha.
Right.
But what about the demographic variables? Their
So,
reliability,
yeah.
okay, that you can measure through kappa, right?
Right. So the equivalent of, or not equivalent, but in the context of your reliability for categorical variables, you use kappa as
Kappa.
against,
And
correlation between.
yeah, and here we don't keep that cutoff of zero point 0.7. We see the correlation value.
Okay.
Okay. So you can see if this value is kappa is 0.047, right?
That's low also. Okay.
So somewhat it is okay.
Hmm.
Okay. So if it is more better, then we can say better. Otherwise, as of now, it's not that much reliable. But we
Correct.
can see this kappa value. If it is zero point 0.5 or greater than that, then it's
I
better.
understand that. It's
Okay.
reliable.
Fine.
Yeah, fine. Thank you.
Similarly, if you have ordinal variables, which is again a categorical variable,
Okay.
right?
Hmm.
And you want to test their, let's say you have ranks, and you
Hmm.
want to test their reliability,
Hmm.
then again in the same, sorry, let me use the recall button, cross steps, statistics. You can use this gamma.
Okay.
Okay,
Hmm.
continue. Okay,
Right.
and and see the value of the gamma.
Hmm.
For ordinal measurement, we use gamma. For nominal measurement, we use kappa, which is also known as measure of agreement.
Now,
And
yeah, sorry.
yes, yes, please.
Yeah, so you said that, say, for example, in Cronbach, of course, there are differing views. Some say more than point 0, point 0.6, 0.6, that is. If
Minimum cutoff is zero point
point
0.6 or somewhere it is mentioned zero point 0.7.
point 0.7 also, right? So
Hmm.
is there any cutoff here also in case of
At least, at
categorical?
least, at least zero point
Point
0.5.
0.5, at
Because,
least.
because, because above zero point 0.5, see
Mm,
that zero point 0.7 from where that theory is coming. That is coming from inter-item correlations. Cronbach
okay,
alpha is nothing but the total number of inter-item correlations with whatever items you have taken, how much they are correlated with each other.
correct.
So zero point 0.7 means 70%, 70% is a strong correlation. That's why we say that the minimum cutoff is zero point 0.7. Okay. So here, even if it is zero point 0.5, that is 50% correlation, we can say that is the scale is reliable.
Is it by some kind of thumb rule or experience or what? I mean, like this, you had zero point 0.7 for Cronbach alpha. Uh,
Sorry?
yeah, it is something to do with the type of the variable, or are these only thumb rules that zero point 0.7 above zero point 0.7 or zero point 0.6 in
No,
case of
that's what that's what the thumb rule I am telling. Zero
that's
point 0.7 is nothing. The Cronbach alpha or any reliability that you are measuring, that
yes,
reliability is nothing but inter-item correlations.
correlation. That's right.
Right?
Yes.
Zero point
Right.
0.7 and above that is considered as a very strong correlation.
Okay.
That's why there we keep zero point 0.7.
Mm,
Here, if you are getting zero point 0.7, fine. If
mm,
you are not getting zero point 0.7, then at least zero point 0.5, because these are nominal variables, right?
that's
Categorical variable. So at least zero point 0.5 and above.
okay.
So if it is a nominal variable, because I don't know how people have been measuring this reliability of nominal. Sometimes they leave it, or
Mm,
sometimes they apply Cronbach alpha, which is wrong. Cronbach alpha should not be applied on nominal or categorical variables. So if your
okay.
categorical variable is nominal, then please use the kappa, which is known as the measure of agreement.
Mm.
Okay.
Oh, got
And,
it.
and if it is ordinal, then please use
No.
gamma.
Okay.
Both these options are available in cross tabulation.
Okay. Thank
So
you.
this cross tabulation helps you to measure the whether there exists association between the categorical variables or not. Then the phi and the Kramers we helps you to understand what is the degree and strength of that correlation.
Yes.
And the gamma and the kappa helps you to establish the reliability
Liability.
of your categorical variables. So from next onwards, whenever you are taking demographic variables into your research, please report their gamma or the kappa value depending on whether you have taken them as ordinal or cut or not. Right? Don't leave their reliability. Their reliability needs to be measured.
Yeah. Mostly in studies, this is kind of neglected.
Either neglected or a wrong practice that people take
Not
this also
not
for
practice. Not
Cronbachel.
practice. Not practice the right word. Yes.
Yeah.
Thank you.
So these should not be measured with Cronbach alpha. These should be measured either through measure of agreement
Mm.
or which is known as kappa method or through the gamma method. Okay.
Thank you. This is wonderful.
Excuse me, sir.
Yes, please.
Sir, is it the same, like this kappa is same as Cohen kappa, which we used for inter-rater liability, or
Yeah, it's Cohen
that?
kappa, nothing. Yeah, same. Inter-rater
Okay, okay, sir.
reliability. Yeah, same Cohen kappa it is.
Okay, sir. Thank you,
Yeah.
sir.
So this is about the cross tabulation and chi-square test. Now next is the correlation. As we know that correlation is a relationship between two variables. How two variables are related with each other. So let's say we have a variable x and a variable y. How are y and x are related? And we model this relationship as every outcome is equal to model plus error. Because none of the outcome can be explained to the level of 100%. So whatever goes explained is due to this error, and the model is the statistical model. In case of correlation, outcome y is equal to Ex plus error, where x is your independent variable and b is the correlation coefficient of that variable. This correlation, always keep this in mind. This formula, every outcome is equal to model plus error. And in place of model, you can put your statistical model. It could be the ANOVA model, it could be the t-test model, it could be the chi-square model, it could be the correlation model, it could be the regression model. So henceforth, we'll be using this thing that every outcome is equal to model plus error. So in our case, the outcome y in correlation is equal to bx plus error, where b is the correlation coefficient of the variable x. Because 100% correlation cannot exist between any of the variable. So whatever goes unexplained is due to the error. And this error happens because of these data points not fitting on a straight line, diverging away from the straight line. So let's say if you are bringing change in a variable x, variable y is also changing in the same direction, then this is known as positive correlation. If you are changing variable x and variable y is moving in a negative direction, then that is known as the negative correlation. Means when the variances move in the opposite direction, then they are known as negative correlations. When variances move in the same direction, then that's known as positive correlation. Here, the negative and the positive value only shows the direction of the relationship. So, if it's a negative relationship, means if x increases, y decreases, or vice versa. If it's a positive correlation, that means that if x increases, y increases, or vice versa. It does not tell us about the magnitude, it tells about the direction of the correlation. So if you see, there is a situation where r is equal to minus 0.9, means 90% correlation is there, but it is negative. Means 100% change in x is bringing 90% decrease in, or if x is increased by 100%, y decreases by 90%. Here, if you see the third case, r is equal to 0.90. That means, and it is a positive correlation, that if x is increased by 100%, y increases by 90%. Or if x is decreased by 100%, y decreases by 90%. Due to negative value, you cannot say that this is low in magnitude. Both are having the equal magnitude, equal strength. Only thing is that their directions differ. If r is equal to 0.00, that means no correlation at all. This is the first thing about correlation that you should know. And it is based on the covariance. So variance means the variation from the mean value. And when you are measuring two variances simultaneously, they are known as the covariance. So covariance is nothing but, you can say, the crude form of correlation, or you can say the unstandardized form of correlation, whereas correlation is the standardized form of covariance. Variance, you are adding a word co, means you are measuring two variations at the simultaneously. The variation of x with respect to, the variation of y with respect to variation of x. If this covariance is in a positive direction, then it is known as positive correlation. If this covariance is in a negative direction, then it is known as the negative correlation. So covariance and correlations are interchangeably used terms. Only thing is covariance is unstandardized form of correlation. And initially you can see this correlation through scatter plots. Already I have told about this outcome is equal to model plus error. If you have to model this correlation, variance, covariance, I have told. Now let's take this example. If you see this example, see the first case. As advertising increases, if you see the first case, if you see the first, second, and the third case, you can find that yeah, as advertising increases, initially the number of packets sold decreases. This is a negative correlation. But afterwards, as advertising increases, number of packets sold of a product increases. So increase in advertising leading to decrease in packets sold is a negative correlation, whereas increase in advertising with increase in leading to increase in packets sold is a positive correlation. So it only shows the negative and the positive only shows the direction of the relationship. It is nothing but this variance and this variance. You are trying to measure two variances simultaneously, and that's what you are measuring, a covariance. And this covariance is nothing but the unstandardized form of correlation. So this is the covariance. If you have to, because the correlation, if you measure XY, then also if you can if you want to measure, you can measure through the X minus X bar, means what is this position of the current mean value with the actual mean value, because there will be a total mean value of let's say you have 200 observations, then each observation will not be equal to the mean value. It will be slightly different from the mean value. So that variance, that is known as the variance of each individual observation we have taken. Similarly, you have taken for Y also, you have taken the difference between the mean and the individual observation. And when you have taken this for all 200 values and summated it and then divided it by total number of observations minus 1, you get the value of covariance. And whatever you are getting as the value of covariance is nothing but it's the correlation value. Is this concept clear? How correlation covariances are?
Sir, would you please explain the covariance example again?
This example,
Yes, sir. Yes, sir.
see, let's take one example. Mm, let's say I'm in my room, okay? It's
Yes, sir.
35 degrees centigrade. The temperature is 35 degrees centigrade. I turn on the AC. As I decrease the temperature on the AC, okay? Or if, let's say, if I increase the that knob of the AC, let's forget about the remote control knob. If I increase the knob of the AC from 2 to 4, what will happen to the time taken for the room to get cooled?
Yes.
Will it increase or decrease?
Decrease.
The time taken
Sir.
for the room to get cooled will decrease.
Yes, sir.
So what I'm trying to measure, the change happening in the knob. Along with that, I'm also trying to measure. So one variance I'm measuring. So initially my air conditioner was set at 2. Now I'm changing it to 4, right? And at the
Okay.
same point of time, I'm also measuring that the mean temperature of my room was 35. Now,
Mhm.
how much time it will take it for it to reach to the 25 degrees centigrade? So two variations are happening. One at the level of the air conditioner temperature, other at the level of my room temperature. Correct?
Okay, okay. Yes, sir.
When simultaneously I'm trying to measure these two variances, this is known as covariance.
Yes,
Okay?
sir. Yes, sir. Now
If
it's understood.
if if this covariance is positive, means as the but here you can see as the knob increases, what is happening, the time taken for the room to reach 25 degrees centigrade
Is
decreases.
decreasing. Yes, sir.
So this covariance is negative in nature.
Yes.
So it is known as negative correlation. So I already told that covariance is nothing but the unstandardized form of correlation. First thing. Now just take another scenario, a room heater or a blower. As I increase the knob, the time taken for the room to get hot will, what will happen to the temperature of my room? It will increase, start increasing.
Yes, sir.
Again, I'm measuring two covariances which are moving in the same direction. This is
Yes.
known as the positive covariance or positive correlation. So when you are changing two things, so bringing change in one thing is a variance. In Y you are bringing a variance, in X also you are bringing a variance, and when you are trying to measure these both variances simultaneously at the same point of time, you are measuring covariance, and this covariance is nothing but unstandardized correlation. If it is in the
So,
same direction, then it is
so sir,
positive.
that means
Yes.
change in, for example, change in X and change in Y, these are the two different variances.
Yes, change in X and change in Y are two different variances When we are
Oh,
measuring these together, then it gives us the value of covariance.
okay, sir. Okay, sir.
You can see this formula. See, this is the first one is the change in x, another
Yes.
one is the change in y
Yes,
from
sir.
its mean value, right? When
Yes, sir.
it's for all observations, when you multiply and summate this and divide it by n minus 1, means total number of observations minus 1, you'll get the value of covariance.
Yes, sir. It's
And this
understood.
value is nothing but the correlation value. As of now, it is in the unstandardized form. The moment you
Yes.
write it as a correlation value, you say that it is the standardized form of the covariance.
Yes, sir.
I hope now I'm clear on this.
Yes, sir. Thank you. Thank you, sir.
Okay. Now, how to decide which of the correlation to test for? So it's very simple that we want to test association between variables, right? Now, if both the variables are metric, the x and the y, they are metric, then already I have told that for metric data, you have to check the first thing that whether they are normally distributed or not. Because non-metric data won't be normally distributed. This only. I never assume that every metric data is normally distributed. That's why if you have a metric data, test for its normality, either by Shapiro-Wilk or Kolmogorov-Smirnov or any of the other method. If it is following normality, then move on to the next step to see whether the sample size is small or large. So let's say at the first step, any one of them is categorical. Any one, not both. Please remember, if both are categorical, then you have to do chi-square. If out of these two, any one is categorical, one is metric, then you have to move directly onto the non-parametric correlation, which is Spearman correlation. If both are metric, then test their normality. If there is no normality, if they are skewed, then Spearman. If they are normally distributed, then move on to check whether it's a small sample size or big sample size. However, sample size is very much related with the normal distribution. If you have a very small sample size, chances are that normal distribution won't be also there. Why we are considering a large sample size for Pearson correlation? Because for a small sample size, you cannot test the change happening at uh, accurately. Okay, so let's say you have a very small sample size, let's say 10 or 20. That won't be able, that 20 observations won't be able to tell you exactly whether the correlation is correct or not. So for that matter, you should move on to the non-parametric correlation experiment. If you have a large sample size, then of course go for the Pearson correlation. Forget all this. The basic requirement is for Pearson correlation. As of now, I'm talking of Pearson correlation. For Pearson correlation, your both the variables, or even if you are trying to measure three variables at a time, four variables at a time, all should be metric. Is that clear?
Yes, sir.
None of them should be categorical. All should be metric. If all are metric, then you can do Pearson correlation. Now let's take an example. Don't know whether we share with you that data. I think exam anxiety. I've said somewhere else. So this is my data set, and having five variables, we will be focusing on these three variables. We have taken the time spent revising by a student, okay, which is a continuous variable. Their exam score, which is again a continuous variable, and their anxiety score, which is again a continuous variable, or metric variable. So all these three variables, because this is the time spent revising, which is interval in nature, exam score, which is absolute values, right? Their anxiety score, absolute values. So all these three are our metric variables. So we want to test a relationship that how these, either you can test how exam and anxiety are related, or how exam and performance, the anxiety of the student and revision are related. We want to test all these three relationships at once. You can do in 2 steps, or you can do all that at once. So the initial test of, so first thing you should be knowing that it's a relatively good sample size, more than 100, large sample size. All these three variables are metric in nature, so we can perform Pearson correlation. Before you move on to correlation, the best test for any correlation is scatter plot. Again, if you want to have an initial look at the data through graph, you can plot a scatter plot. So you can go to analyze, or it's a graph, legacy dialogues, and from here scatter. So click simple scatter, define. So on y-axis, let's say I'm taking exam performance, and x-axis time spent. Okay. So these are the plots, but it doesn't give you a very good interpretation. So double click and fit on a straight line. So this is there is one fit line at total. Add fit line at total. Now by seeing this, you can say that when you are plotting the relationship between time spent revising and exam performance, there is a positive correlation. As time spent revising increases, the exam performance also increases. Okay. Similarly, you can plot a relationship between exam performance and exam anxiety. Fit line at the total. Here you can see that there is a negative correlation. As exam anxiety increases, exam performance starts decreasing. Isn't it? Do you agree with me?
Yes, sir.
So this is an initial exploration, which will tell you about the direction of the relationship. But what is the strength of this relationship? So this is exploratory graph, exploratory data analysis to see that whether there is some correlation among the variables or not. Now let's do a Pearson correlation. So go to analyze, regression, and Pearson is the kind of correlate. Pearson is the kind of bivariate correlation. So take the variables. So time spent revising, exam performance. You can take 2 at a time. I want to take all 3 at a time. And here, by default, Pearson is selected. Test of significance is two-tailed. So my null hypothesis is there is no association among the variables, and alternatively, there is some association. Okay. Now, if you see this, the first one, time spent revising with exam performance. Never try to correlate time spent revising with time spent revising. Time spent revising with exam performance. This is the first. Let me tell you the cutoffs. So up to 25% is a weak correlation. 26 to 50% is moderate correlation. 51 to 75% is strong correlation. Greater, greater than 75% is relatively. You can use your own term: weak correlation, moderate, moderately strong, very strong. You can use, but this is ideally the cutoff. Now, if you see time spent revising with exam performance, the relationship is positive or negative?
It is positive.
So time spent revising and exam performance are positively related. And what is the correlation coefficient?
So moderate it is.
It's 0.397,
Yes.
39.7%. So
Yes.
there is a moderate positive correlation, right? So what we can write? R between time spent revising, just for our, and exam performance is equal to 0.397. Hence, there is a moderate positive correlation of time spent revising and so if the time spent revising is increased by 1 unit, exam performance also increases by 0.397 unit. Or you can say, because time spent revising is in hours, so if I think number of times, its unit is time spent revising, yes, number of hours. If a student's revision time is increased by 1 hour, the score will increase by how much? 39.7%, right? Now see the relationship between time spent revising and anxiety. There is a negative correlation and very strong correlation, isn't it?
Yes, sir, 70%.
Yes, sir.
70.9%. So you can say R T and anxiety is equal to minus 0.709. Hence, there is a negative correlation among time revising and exam. You can see that if a student revises one more time, or if the revision time is increased by 1 hour, the anxiety score decreases by 70.9%, and exam performance increases by 39.7%. Now the third thing, the relationship between exam anxiety and exam performance. Anxiety and exam performance. Equal to how much? Minus 0.441.
Negative 44%.
Yes, sir.
Minus 0.441. Hence, there is a moderate negative correlation between exam anxiety and exam. So from all this, we can say, now you might be saying that why I have modeled all these three at once? Why not first between time spent revising exam performance and anxiety, then anxiety and all? Because please remember the golden rule, outcome is equal to model plus error. Similarly, in case of ANOVA also, I have brought in three variables. Rather than doing ANOVA, you can do independent t-test. First to second comparison, then second to third comparison, and first to third comparison. But where the problem is, if outcome is equal to model plus error, and if I'm calculating the outcome three times, then what will happen? Outcome 1 is equal to model 1 plus error 1. Outcome 2 is equal to model 2 plus error 2. Outcome 3 is equal to, that's why I'm talking of this thing, model 3 plus error 3. Is this a good estimate of statistics, or this one is a good estimate of statistics? Which one is a good estimate? Getting error three times or getting error only one time?
One time.
Yeah, that's why we try to model all our variables at once, if you have many variables. So now if you see at this, so there is a moderate positive correlation among time spent revising and exam performance. So if revision is increased by 1 hour, exam score increases by 39.7%. If a student revises by 1 more hour, the anxiety decreases by 70.9%. Standalone anxiety has, if exam anxiety increases by 100%, exam score decreases by 44.1%. Means anxiety affects the performance negatively. But what is happening here, if you see the entire relationship, if the students revises more, anxiety decreases. Anxiety decreases. So in turn, what is happening? If anxiety is decreasing, what
Performance
is happening?
increases.
The
Performance
performance
increases.
increases. So if you have to write the interpretation of all these three, you can write that as a student revises more, their anxiety decreases, and due to the decrease in anxiety, what is happening? The exam performance increases.
Increasing.
Because anxiety and exam performance are negatively correlated. Is the interpretation clear?
Yes, sir.
Any questions on this? So at one go, you can write the interpretation that as student revises more, their anxiety decreases, and if anxiety decreases, their performance increases. So one unit of revision is leading to decrease of 70.9% of decrease in the anxiety, which in turn is leading to 44.1% of increase in the exam performance.
Sir, there is one doubt.
Yes.
Sir, as you said earlier that the outcome is equal to model plus error, and also you
Mhm.
said that if there are different, you make different equations, then you will have more error. So it
Mhm.
is good that you make one equation and the error will be less. So, sir, where
Mhm.
is that error in this example? As you perform this correlation.
No, I'm modeling all at once. If you could see, I'm modeling all at once. I'm not modeling them separately.
Okay.
So for me, this outcome, that is exam performance, is equal to uh, what is the B value of this anxiety minus 0.709 into anxiety plus 0.441. I'm sorry, into
Minus.
no no into plus 0.441, not no no, time spent revising plus 0.397 into revision. Okay,
Okay. Okay.
getting this? I have modeled all at once. Otherwise,
Yes.
three times the model could be outcome is equal to minus 709 into anxiety plus error. Outcome 2 is equal to 0.397 into revision plus error. Right?
Yes, sir.
So like this. So again, it will be more error. So I have modeled all the equation at once. Means all three variables I have done the correlation at once. So that's why I'm saying that what is happening in our case, that as the students revises more, their exam anxiety decreases, and because there is a negative correlation between the exam anxiety and the revision, in turn the exam performance increases,
Increases.
and that's also cross validated by time spent revising and positive correlation between exam performance. Right?
Yes, sir. Now it's understood.
Understood?
Yes, sir.
I'm modeling all three at once. This is Pearson correlation. Now, if one of the variable out of this, anyone, others are continuous or metric, one of the variable is categorical, and in that categorical, it is in the form of ordinal ranking. Okay, it is ranked. Then rather than using Pearson correlation, we use the non-parametric of Pearson correlation, which is known as Spearman correlation or interclass correlation. So for that, I will be using a separate data. The biggest liar.sap. So I have a hypothesis, and if you can see here, the sample size is small. So I will be focusing on these two variables, creativity and position. So I have an assumption that people who are more creative, they are very good in telling stories. And if they are very good in telling stories, then they have higher chances winning a liar competition. They turn out to be better liars. So my assumption is people with more creativity turn out to be better liars. Are you getting my problem statement? This is the relationship that I want to model.
Yes, sir.
So what I have done, I have asked 64 people, 68 people to write an exam based, which was a creativity, which would test their creativity skills. And out of this, they have got the scores, the numbers. This score you can see is the absolute value, so this is metric variable. Clear? The creativity score is a metric variable.
Yes, sir. Yes, sir.
Based on their score, they have been ranked first, second, third, fourth, fifth, something like that in that competition. The competition name is the biggest liar. Because my assumption is that people who are more creative turn out to be better liars. Means they will get better position in the biggest liar competition. So they have been asked to take a test to judge their creativity skills, which has been given some numbers. Okay. And then based on this score in the exam, the creativity score, they have been given the position in the competition as first, second, third, fourth. Is this situation clear?
Yes.
So one variable is a continuous variable, another variable is a ordinal rank variable. This position is a ordinal rank variable. So I want to find the relationship between creativity and their position in the competition. To find out whether to test a hypothesis, my null hypothesis is more creative people are not better liars. An alternative is more creative people are better liars. Or there is association between creativity and person winning in a lying competition. Is the problem statement clear?
Yes, sir.
Sir, would you please repeat the null hypothesis again?
Or you can write creativity has no association. Creativity has negative association. Is this clear?
Sir, in this null hypothesis, you wrote that creativity has negative association with the line capacity.
Or no relationship. You can say no relationship. No association. Here you are saying creativity has positive association. Or there is association. Is that clear?
Yes, sir. Yes, sir.
Sir, I just had one doubt. In
Or
the
forget about this all hypothesis. Simply, I want to say that based on the creativity, I want to find out what is the position of the people based on assumption that more creative people are better liars. Okay? Let's keep it one tailed. Yes, yes, please.
No,
Yes.
sir, it's okay. Please continue. Thank you.
No, you had a question. Please ask.
Okay, so I was just wondering in the introductory class, um, if I understood it correctly, usually null hypothesis is something which is related. So direct association, we keep like that. And alternate hypothesis, we keep like there is no association.
No, I said that null hypothesis is the negation of existing theories,
Okay,
whereas alternate hypothesis is opposite of the null.
okay,
Okay.
sir.
So
Okay,
first you
sir.
frame the null. So many studies have confirmed that people who are more creative are better liars. I am saying I don't agree with this. Creativity has nothing to do with the line competition,
Hmm.
line capacity. Then I made opposite of it that creativity has something to do with the line capacity, right?
So based on literature, whatever we understand, the negation of that, we keep it as null hypothesis as a
Yes,
general
yes,
rule.
yes, yes, yes. Because see, that's a very wrong notion that null hypothesis always has to be a negative state. It is negation of existing theories. If you are already agreeing that yes, I agree that the existing theory is correct, then what is the point in testing it? That's why we test the null hypothesis. We never test the alternate. We test the null hypothesis by saying I do not agree to this point, and let me check whether it is correct or not in my side.
Okay, sir. Okay, sir. Thank you, sir.
So
Yeah,
in my
but sir,
case, I am saying, yeah,
in this at this time when we like write a paper, then uh, we frame hypothesis like as an alternative hypothesis. So,
which one, sir?
sir, like as we write paper, in this time we write a paper, then we write only alternative hypothesis in the paper.
Please remember that is not alternative hypothesis. That is one-tailed hypothesis,
Yes, sir. Yes, sir. Yes, sir.
not
Exactly. Yes, sir.
alternative. Because if you are saying alternative hypothesis, it has to be a null also accompanying it.
Yes,
So
yes,
only
yes.
one hypothesis you are finding, that means you are very sure that this is bound to happen, and you are framing one tail.
Yes,
That I
sir.
think I have explained in the first class. But
Yes, sir.
when you are not sure, then you frame a null hypothesis negating the existing fact, and then you also formulate an alternate hypothesis. Okay,
Yes, sir.
that is the two-tailed hypothesis. What you are saying is not an alternate; it's a one-tailed hypothesis.
Yes,
Naming
sir.
at
Yes.
H1, H2, H3, H4 doesn't makes it alternate. I am saying
Mhm.
it's hypothesis 1, hypothesis 2, hypothesis 3, right?
Yes, sir.
Okay, that is one tailed. So I already told that the better idea when you are not sure, please make a one, because this is what I'm running an experiment. That's why I'm putting two-tailed hypothesis. Okay.
Yes, sir.
So what I did to test this, that whether creativity is linked with line capacity or not. What I did, I asked people to give a test, and then based on the scores, I gave them a rank in the liar competition. So the person who is scoring the less, that is one, is the topmost position holder. Then second, then third, and fourth, and so on. Right?
Yes, sir.
Yes,
Clear?
sir.
Situation clear? So one is the continuous variable, another one is the categorical variable, which is ordinal ranking. Right? So in that case, the association cannot be tested by Pearson. We have to run Spearman. So analyze, correlate, bivariate, and here you put position in the best layer competition and creativity. And rather than Pearson, you have to select Spearman. Okay. What is the relationship between them?
So it is negative.
There is a
Negative 0.373.
what does this means?
That means the students who are more creative are not a good liars or better
No,
liars.
no. See, this is position in best layer competition. This means that
Yeah.
if creativity is increasing, their position in the best layer, their rank is decreasing, right?
Yes, sir.
And if rank
Oh,
number
okay.
is decreasing, what is happening?
Yes, sir. Yes, sir.
They are moving from 3 to 2, 2 to
Better
1,
position.
better
Yes,
position.
yes.
Are you getting my point?
Yes, sir. Yes, sir.
See, this is position in the best layer competition. If the creativity is increasing, what is happening to their position rank, the number in the rank?
It is decreasing.
It is decreasing. If it is decreasing, that means they are getting better positions,
Exactly.
moving from 4 to 3, 3 to 2, 2 to 1, isn't it?
Yes, sir.
So the person with the highest creativity will get the rank of 1.
One.
Means if person is more creative, then they are better.
Better liars.
So if this is a situation where you have a continuous variable and an ordinal rank variable, then you should perform Spearman correlation. That's why it is known as inter-class correlation. Okay. Now,
Yeah.
here I have done one thing that is wrong. See, there are many ranks tied ranks. You can see many people are getting 1, many people are getting 2, many people are getting 3, isn't it?
Yes, sir.
Yes, sir.
Then the better test is not Spearman. The better test is Kendall Tower. Spearman should be used when every individual have individual rank, when there is no tie between the rank. For example, people coming first, second, third in a race. 2 people cannot come first in a race, isn't it?
Yes, sir.
So first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10. Let's say you want to find a relationship between their height and their chances of coming first or second in a race, or the length of the legs and chances of coming first in the race. So somebody will come first, second, third, fourth, right? No 2 people will come first. There won't be any tie. If there is no tie between the ranks, then only we should perform Spearman. Okay. If there is a tie between the ranks, then we should perform which test?
So, Kindle.
Kendall's Tau.
Kendall Tau. So both Spearman and Kendall Tau is applied when one of the variable is ordinal rank. But please keep in mind, if ranks are tied, then we use Kendall Tau. If ranks are individual observations, then we use Spearman. Is the difference clear?
Yes, sir.
So here we will use Kendall Tau rather than Spearman. And this is our correct result. There is a 30% negative correlation between creativity and position in the biggest layer competition. So if a person creativity score is increased by 100%, their position decreases by 30%. Means more the creative they are, their rank in the rank number is decreasing, means high creativity score means less number rank, like one or two, and person is turning out to be a better liar. Their position is improving in the better liar competition. Is that clear?
Yes, sir.
Only thing that you have to keep in mind that if you have the outcome variable, if you have one of the variables uh, in the form of ordinal rank, and see, first, if both your variables are categorical, then of course you have to go for chi-square. If both are continuous, then you have to go for Pearson. If any one of them is categorical, and that too in categorical, it has an ordinal rank, any one means the another one will be continuous. Then you have to go for either Spearman or Kendall Tau, depending on what kind of ranking it is. If it is individual rank for every individual, then the Spearman. If ranks are tied, then Kendall Tau. Is that clear?
Yes, sir.
Now what if one of the variable is continuous, and in that continuous it is is categorical, one is continuous, another one is categorical. I have told you about this one, uh, ordinal rank. What if it is dichotomous, like S no, male female, low high? To want, if you have one variable like that, another one is continuous. In that case, we use the biserial or point biserial code. So please remember the rule. I'm just writing it here just for your remembering. Both variables categorical, both variables, both yes, both the variable also I'm talking, both variables continuous or continuous correlation. One of the variable is non-metric. German or ICC, German interclass class code.
Sir, can you repeat ICC? That is interclass correlation, correct?
Yes. German, like we call Pearson correlation as Pearson product moment correlation in statistics. Similarly, we call Spearman as interclass correlation. Dichotomous means yes or no. Another one means another one is continuous, right? Yes or no, male, female means divided into two categories. That you can write. Now here there is one confusion. I'm saying dichotomous, two categories, and then I'm saying there is a discrete dichotomy, which means both of the categories have no connecting point in between. When there is a when there is a dichotomy, of course they won't have a connecting point between them. But on the other hand, I'm saying there's if there is a continuous dichotomy, means if there is some connecting point between the two categories. For example, say this case of continuous dichotomy is very rare, very less. You have two categories, but there is some connection between them, some continuity between them, which is ideally practically very less. For example, fail and pass. Let's say if the passing mark is 40, somebody got 39.5. He failed the exam. Somebody got 40.1. He passed the exam. They are failing or passing by very marginal numbers. So there is a continuous dichotomy between the fail and pass. Are you getting my point?
Yes, sir. Yes, sir.
Like male, female, and transgender in between. There is a connecting point. Then continuous dichotomy. Discrete dichotomy is a situation which is mostly, because if I'm talking about dichotomous, means there won't be connecting link. Like living and dead. Have you heard of somebody being called as half dead or half living? Medically, nobody is either half living or half dead. Either he is dead or living. A person in coma, we call it, or somebody unconscious, we say half dead. But medically, they are not dead. Medically, they are alive only if they are completely dead. So there is no connecting link between living and dead. Are you getting my point?
Yes, sir.
See, the cases of continuous dichotomies is very less examples. Means when you find some connecting link between your categories, like I have given the example of pass and fail. Somebody is passing by 0.1 mark, somebody is failing by that 0.1 mark. Only a little bit of differences between the dichotomous variables. Okay, that is known as continuous dichotomy. Discrete dichotomy is when there is no relation between both the categories. Means both are equally opposite to each other, right? Dead and living, right? So, if there is a case of discrete dichotomy or perfect dichotomy, then we applied point by serial correlation. So, first thing is that there should be a dichotomy. One variable should be dichotomous, another one will be continuous. In that dichotomy, if there is a discrete dichotomy, then we write point by serial. We use point by serial. If there is a continuous dichotomy, which is very less, then we use by serial. Method is same. Method for both is same. Only we quote it as RPB is equal to, like R we quote, here we quote RPB. Denote by RPB. That means point by serial means there is a discrete dichotomy, or RB means by serial. That's the only difference. So for that matter, I'll give you one example. So this is the gender, male and female, where 1 stands for male and 0 stands for female, and time spent out of home. Time spent out of home is an interval variable. Gender is a dichotomous variable. Okay, only male and female I'm taking. Okay, and I want to see, is there a relationship between gender and time spent out of home? Are you getting the problem statement? One is continuous, one is dichotomous. And I want to establish a relationship that is gender is related, because if this would have been categorical, then we can apply correlation. But since this is continuous, we cannot apply chi-square. So what I'm trying to say, one is dichotomous, another one is continuous. So I want to establish a relationship that how gender is associated with time spent out of home. Right? Getting
Yes,
the
sir.
problem? Okay. So I'll apply
Yes,
the
sir.
point by serial correlation, go to analyze, same bivariate, Pearson only you will take. There is no other method. But you will quote it as RPP, time away from home, gender. Okay. What is happening here? There is a positive correlation, isn't it?
Yes, sir.
So what does it say? As the value of gender increases, time spent out of home also increases. Value of gender increases means it is moving from 0 to 1. And 1 means male. So
Yes, yes, sir.
male spends more time out of home as compared to females, isn't it?
Yes, sir.
As the value number of gender increases from 0 to 1, time spent out of home also increases because there is a moderate positive correlation, means male tend to spend more time out of home. This is the relationship. Now, if you want to check it again, I have recoded it. All 1 as 0. Now, 0 stands for here male. Here 1 was standing for male. Now I have recoded it. Reverse it. So now 0 stands for male and
Females.
1 and no. Here 0 stands for
Males.
males.
Okay, okay.
I have
Yes.
reverse ordered it, recoded it. Now here 0 stands for male and 1 stands for female. Okay.
Yes, sir.
And again, if you analyze, gender recorded with this variable, there is a negative correlation. What it is saying? That as the value of gender decreases, time spent out of home increases. There is a negative correlation now, isn't it?
Yes, sir.
Same value with negative correlation. The moment I have recoded, it is giving me negative correlation, saying that as the value of gender, what is happening? Decreases, time spent out of home is increasing because there is a negative correlation. And if the gender is decreasing, that is meaning it is moving from 1 to 0. Again, here when we have recorded, 0 stands for male. So here also, in this case also, male spends more time as compared to females out of home. Either you do by this or, oh, sorry, not this one, it was this data. Or if you record it, this was 0 as female and 1 as male, and if still you do, you will get the same value but negative. That means as gender decreases, the value of gender decreases, time spent away from home increases. Means as it moves from 1 to 0, time spent out of home increases. And in this case, 0 is male. Again, the same result, male tends to spend more time out of home. Is that clear?
Yes,
Just
sir.
to explain you, I have recorded. Otherwise, only through first two variables you can find out the result. And I will quote it as RPB is equal to 0.37. Is significant. Correlation is significant. It is point by serial correlation, means there is a discrete dichotomy, and one of the variable is dichotomous. Is that clear?
Yes, sir.
Okay. Now, the partial correlation. We do the partial correlation when we assume that one of our variable is affecting the relationship and we are not getting the correct relationship. Like we all know that exam and anxiety were negatively related, but somewhere this relationship was affected by revision time, isn't it?
Yes, sir.
What if we want to calculate the exact relationship between exam and anxiety while controlling for revision? It is the same example case, like We all know that at 100 degrees centigrade, time is time taken for a water to boil. 1 liter of water to boil is 2 minutes, right? And if we increase the temperature to 200 degrees centigrade, this time will decrease to 1 minute. But will it stand true in all the cases? You have taken 1 liter of water at 100 degrees centigrade, it is taking 2 minutes to boil. The moment you increase the temperature to 200 degrees centigrade, the time taken to boil decrease to 1 minute. But will this case be, there is a relationship that as temperature increases, time taken for water to boil decreases by 1 minute. But will this stand true in all the cases? Yes or no?
No, sir.
Will this stand true for a 2 liter water?
No, sir.
Will this stand true for a ice cold water? Not at all, right?
Yes, sir. Yes, sir.
Because this relationship will also be affected by what was the initial temperature of the water, isn't it?
Yes.
So what you need to do, you know that this initial temperature is affecting this relationship. So you have to control that initial temperature. Means all the samples that you are taking, you have to take at the same temperature, initial temperature. Or you can say at the room temperature, then only you can say that this was the time taken for the water to boil at a given temperature. Given the initial temperature of the water was controlled and it was kept at room temperature. Are you getting my point?
Yes, sir.
So if you want to do such situation, then we do a partial correlation. So similarly here, there was a relationship between exam and anxiety, but this relationship was affected by the revision time. Okay. Now we want to find the exam relationship between anxiety score of the student and their exam performance while controlling or standardizing their revision time, making this revision time as a constant. In that case, we will do a partial correlation. Are you getting my point?
Yes, sir.
So go to analyze. Means whenever you feel that there is a third variable which is affecting the relationship, you want to control that variable, then we go for partial correlation. So analyze, correlate, partial. So here I will choose time spent review. No, sorry. Exam performance and exam anxiety. And if I control the time spent revising, then it will give me the clear picture of what is the exact relationship between exam and the anxiety. When time spent revising is standardized for all the participants, all the students are controlled. Okay. Now you see what is the relationship between exam performance and anxiety.
Minus
Twen-
0.247.
What was the previous value? 0.441.
It is, yes, sir.
0.441. Exam anxiety and performance, it was 0.441. Isn't it?
Yes, sir.
Initially, it was 0.441. But when you controlled the time spent revising, the relationship between exam anxiety and performance has decreased to how much? 24.7. From a moderate relationship will remain negative, but from a moderate relationship, it has become the weak relationship. Are you getting my point?
Yes, sir.
So now the relationship between exam performance and anxiety while controlling for time spent revising is measured. Then we found that from moderate negative correlation, it has decreased to weak correlation. Because this time spent revising was affecting this relationship, so we controlled it. We made it standard for all the participants. And in such case, we have got the relationship between exam performance and anxiety, which is now minus 0.247 or 24.7% negative correlation. And this is actually the correct relationship between exam performance and anxiety in presence of time spent revising, when this time spent revising was controlled. When it was uncontrolled, then the relationship was this much. For every individual, it was different. So it was showing this much correlation. When it was standardized for all, then it decreased to 0.247. And this is the exact relationship between the performance and anxiety. So whenever you have a third variable affecting a correlation and you want to standardize that third variable, then you control that variable and perform a partial correlation. You are not removing that variable. That variable is there, but it is throughout standardized for or made constant for all the participants. And in that case, for all of them, the relationship between exam performance and anxiety will be 24.7% negative. Is this clear?
Yes, sir.
Yes, sir.
So this is all about the test of associations today. I hope I have answered most of the queries. Still, if any queries left, you may feel free to ask. Most of the